Well, yeah, Jousef, thanks for inviting me. So today I want to give you a quick overview on how to train a graph neural network on CFD data and how we at Navasto do it. And I'm going to start with a quick introduction of the company and our vision. And maybe I'll start with myself. My name is Jakob Lohse. I've been working for 7 years now at Navasto. And basically, I work between the customers and our internal method development to make sure that everyone has everything he needs. And Navasto is not actually a startup. So it was founded in 2014 by two engineers, and then it grew slowly to more than 20 experts in engineering and AI. So it's a mix of physics, engineers, AI specialists, software developers. And during these more than 10 years, we saw the growing potential of machine learning applications in CIE workflows, and we saw how they can accelerate them. And in all this time, we try to really accelerate engineering processes using AI, and we're doing this for a lot of large companies. All of our customers are much larger than ourselves. Most of our customers are working in the automotive sector, but we also have some other customers, some integrations like SimScale, also some Formula One customers, but they all share kind of the same vision, and that is that you can really put people from different disciplines together in one room, and they can work together, and they are able to make decisions in this room, and they don't have to postpone these decisions on a product because they simply have to wait for additional simulation results and stuff like this. So the basic example is really, if I can put this picture in your head, this was what was the case for us almost 10 years ago, that an automotive designer and an aerodynamic engineer are really in one room, and they can interactively work together. And the measure how we want to achieve this is really through the usage of AI models. And if you want to do something like this, it's a two-stage approach. The first stage is always you need to train an AI model, and you can do this on different variants of your product. I have a lot of examples from automotive because this is our home turf, so to say. And if you talk about different simulations, usually the geometries vary between these simulations, but also some parameters like fan speeds, inlet velocities, ambient temperatures, whatsoever. Everything that varies is good and can be used to train an AI model. And if you want to use this model, if you want to work then interactively together, you simply give a new input to that existing model. And the nice thing is that you get all the results you trained on, like flow velocity, pressure on surfaces, also scalar values like drag and lift, within milliseconds. Now this enables you to do really nice interactive design together. And if you want to do something like this, you need to find the best AI model, because AI model is like a large word, but for different purposes, at least this is what I'm convinced of, you need to find the correct model that does the job. And when I started creating machine learning models or AI models for customers, usually they needed to work on data from one project, and most of the time it was really a parametric problem. This was, I would say, like 8 years ago, this was like standard in the industry. So we used to build reduced order models, which is a POD method. And if we had a case like this, the problem usually looks like this. Imagine someone wants to optimize an active rear spoiler. So he says, okay, I want to move the spoiler in X and Z direction. Maybe, of course, I want to change the angle of attack. And maybe I also want to morph the rear diffuser. So it's a parametric problem, which is described by 4 geometric parameters. And then people start sampling this parameter space or this design space. And they say, okay, usually I start with some space filling samples, be as smart as possible, maybe do a Latin hypercube sampling or Sobol sampling, Horton sampling, whatever does the job. And then I run some adaptive sampling or some surrogate-based optimization. Depends a bit what you want to do at the end. And we said, okay, we want to take all these samples and not throw anything away and build a machine learning model really on the parameters. This was our starting point. And then you can get something like this. So you see, like on the left-hand side, you see some sliders, because the new input to a parametric problem is always a parameter. And then you can change the sliders and you get instant predictions for the new geometry, the flow field, and also for the scalar values, which is a super nice thing. And you see that this is in real time. Changes are real-time capable. So you can imagine like the designer and the aerodynamicists sitting in one room together, playing around, finding the optimal configuration. And yeah, immediately also understand why different behavior shows leads to different results, and you know exactly what's worth fighting for and what's not. This was like a starting point. But if you use such a simple method like a reduced order model, which uses a POD method coupled with an interpolator, you have certain requirements which you need to fulfill. And one thing is you need a consistent parameterization all the time. You cannot simply add or delete some of the parameters. And you also need a consistent mesh to make these 3D predictions here. This is really important. And then when time moved on, people said like, okay, I want to create machine learning models because I want to do this real-time design space exploration, but I don't want to create the data freshly. I want to combine different projects from the past. And that's where we at Navasto moved to deep learning functionalities. And I like to give this example when people say, okay, I had this rear spoiler project. I did everything, was perfect, but then someone said like, okay, I work on the same car, but without an active rear spoiler. But basically I have data where I varied everything else on that car. So, and then someone said like, okay, I mean, all these simulations, all this data is created for sedans, and I have another sedan, which is a different model. It's more complicated. So you see like it has an exhaust system, engine bay flow. And the problem is you cannot bring all these different simulation results onto a consistent parameterization, and also not on a consistent match. So you need to really go into deep learning. So you have to create an AI model which uses really the geometries as an input. And there are different technologies like a CNN, convolutional neural network, a PCT, a point cloud transformer. But we at Navasto like to use a GNN, which gives you like a lot of flexibility and works directly on the tessellated surfaces that are also usually the input for a new simulation. And the nice thing is what you can do with this is you can create new inputs very easily. For example, using Blender, we have a small plugin for this, where you can start with setting up a view, like spawning some planes where you want to get some predictions, in addition to the surface predictions on the car. And if you click the predict button, you get instantaneously the same results. Drag value, surface values, like the velocity on this planes. And once you set up your view, you can like really prepare to start working, because as you remembered, I said like the new input is really a new geometry. So you can work directly on the nodes and the edges of your input geometry and manipulate them. So you have like a lot more free possibilities, how you can operate, how you can generate new inputs. And you see like if you click the predict button, you instantaneously get like a new drag value and a new flow field. And this is like, I would say the next step. And since you operate on these meshes and if you use a GNN, you don't have to mess around with like, you need the same number of points or anything like this. That's super nice. And of course you can also play around with an active rear spoiler as you did in the parametric problem. That's very nice. Right. So this is the idea. And if you train a model quite well, you will also see like that the prediction quality is really, really good. And this is something I want to focus on today. So if you have something like this in mind, say you want to train a graph neural network, which predicts the drag and maybe also some flow field quantities, some variables for new geometries, and maybe you want to visualize everything in Blender, what is it that you need to address? Which steps do you need to take? What is it that you need to think of? And so just some bullet points. So again, if you work in a machine learning environment, you always need to think in terms of inputs and outputs. This is the most important thing. And I think in this case, it's quite clear. The input is a new geometry. The output is like obviously some scalar values, drag or lift, and some variables, some flow field variables like velocity and pressure. So this is something that needs to be available. And when you're clear about inputs and outputs, you think about to choose which machine learning model. And yeah, I think you noticed already my favorite is like a graph neural network, because it can handle different types of inputs and outputs. Prediction accuracy is usually very, very good. And you don't have to fulfill these requirements, these limitations, like you have with a POD-based method. Right. And then usually what's available? We think about CFD data as an input. So let's say I have a data set which consists 250 CFD simulations, which are made maybe from different design of experiments, different parameterizations, different kinds of cars. But what we usually see is that if you do a proper CFD simulation, it has something like 120 million cells, and a mesh like this will never ever fit on a current GPU. This is why you need to address this issue. And yeah, with the Navasto software integration, we have some filter pipelines where we can pre-process all these simulations to make them, let's call it machine learning ready, but I'm going to focus on this point a bit later. Just an example, usually a pipeline would look like, I want to exclude everything I really don't need for my model. Maybe I extract some slices or some regions of interest, and I would also decimate the mesh to a certain point. Right. And then let's say, if I think about, I want to make some predictions for new inputs, I want to do the inference not on a CFD mesh. I want to really use like the input a new designer would have. So like a new input that maybe like a designer would put into Blender or an Autodesk Elias. And this should solve as the input for every prediction. So I need to address this in the training. And I think it's like always an easy solution. So we map our CFD results on the required input, and so we can use the same input for the simulation and the machine learning pipeline. So basically, a user can decide whether he wants to run a simulation or he wants to do a prediction from a machine learning model. This is something, you need to think of if you really want to use a GNN workflow in an industrial environment, right? And usually, this whole process is also divided into 3 steps. First step is the pre-processing. Second step, model training, and then inference or running a prediction. And during pre-processing, it's quite simple. You need to collect all the inputs and outputs basically from where they are, because 250 CFD simulations can really take some storage space, so you don't want to copy them to anywhere. Just collect everything so that at the end you have like the mesh, the results, and everything I would refer to as metadata. And this is something we simply save in a decimated machine learning ready form. For the model training, I think quite easy. First, you need to fit your graph neural network, and then you save the model simply to the hard drive, and then use it for inference, where we predict for a new input, which we basically bring together with the saved model. And when we run a prediction, this is something we also can discuss in detail. We can decide what we want to save, because we can save like the full 3D object. We can also just make some images for a plot report, whatever we like. So at the end, it's like you can imagine this process of training and using a graph neural network on CFD data as like a pipeline where you just combine different building blocks that you need to make this process happen. And this is why we also decided to to create quite a flexible product. So our Navasto product is really a Python API, which we call NavPack. So you can imagine it like a library which stores all the functionality that is necessary to pre-process the data, to train a graph neural network, and to also run the inference and do everything that adds value to a customer workflow. And I mean, if you have all these functionality, all these building blocks, you can combine them like Lego. This is maybe a good picture, and you can use these building blocks to create custom workflows. This is something I can show you, but you can also derive some custom browser apps using these building blocks, or some plugins like you saw with ParaView and with Blender, because I'm quite convinced that, I mean, since computer-aided engineering workflows, they are usually quite complicated, and also the tools that are required to really run the simulations and create all this data is already, it's challenging, it's complex, and so we try to really adapt to these existing and validated processes with our large customers, because I'm truly convinced that people cannot easily change these workflows. It would require like years and millions of dollars to do this. So we try to adapt as good as possible to the existing workflows, use the existing data as it is, and make the best out of it. And maybe let's dive a bit deeper to the first of the three steps, the pre-processing. So usually first step is quite straightforward. You simply load your simulation case. And if you load a simulation case in an automotive sector, usually it looks like this. So you have like a large computational domain, and somewhere in between, barely seeable, is like the car. And this is a best practice that is necessary for running the simulation, but not for us. So as I said, like we try to, after we load it, so we can do it like really in a workflow and use these building blocks. If it's Nsight data, we load it like this. If it's VTM data, we load it like with a VTM loader. So we just replace one thing. We can also load directly OpenFOAM or LS-DYNA, whatever is necessary. But the interesting thing is really to manipulate this simulation case. So first thing is we want to remove unused blocks, because we say like, okay, what is changing is really the geometry of the car. So we can get rid, for example, of the internal mesh. It's like just the next building block, next Lego block. So once we did this, we just got rid of all these, surroundings about the computational domain, and we just like extracted the surface of the car. Next thing is like, okay, we need to address like the correct mesh size. As I said, like an automotive designer would never work with like 5 million or 4 million points on the surface of a car. The amount of mesh is like, amount of points is much lower. So let's say we want to decimate the car to 30,000 points. So simply apply like the next filter in the pipeline and reduce the size of the mesh. And then, as I said, we want to also predict maybe surface variables like the pressure. So we have to map these results on the decimated mesh. Simply the next block is like running a mapper, fit it to the source, map it on the target, and then we have like at the end some condensed information, really the surface of the car, the geometry that describes also like the performance, and we mapped the simulation results from really, I don't know, a lot of million points to this 30,000 points, and we fulfilled two requirements. Firstly, the geometry is captured correctly, so we don't lose any features. And the second important point is we can also map the pressure field. We can capture all these gradients with the mesh size. This is why you need to really put some effort into this, so that, let's say for a flat surface, you don't just end up with like two faces. Right, at the end, like we save this decimated snapshot, and usually it consists again of a mesh, some results, and some metadata like drag and lift coefficients. And also this is like really has the size of, let's say, 10 megabytes per sample and not 60 gigabytes per sample. This is quite nice. And we use these preprocessed data for the next step, the training of the model, where again we load the preprocessed snapshots, We define all the in and outputs. We define some training parameters for the graph neural network because this has a lot of free parameters. And then we fit the GNN and save the model. I mean, this is quite straightforward. These are the steps. And I mean, you have to define a lot of things. This is why we said like, okay, you can do it in different ways. You can really like write a Python workflow that uses all these building blocks. You can also say, okay, I have like a high level workflow that just has a configuration file where I can set up everything. This is also functionality. It depends a bit on your personal preference. So at this point, we simply say like, okay, we want to learn node variables, pressure, velocity, and we want to learn also some global variables like these force coefficients. And then we could set like a lot of model hyperparameters with depths, message passes, everything like this. But I mean, I'm not sure how many of you already trained a graph neural network. It's quite complicated since these model parameters, these hyperparameters of a graph neural network are disentangled from each other. So if you would like to optimize them manually, this would take, I would say, years. It's like, I would strongly not recommend doing this manually. I would really always run some algorithms that do the job for you, that do a model selection. I mean, spawning really thousands of models, like it's like a Monte Carlo search, and then really give you some information which models perform best for your specific problem. And this is something we also do. We like to use the Usher algorithm, which basically spawns a lot of models, train them for a short period of time or like a short amount of epochs, and then really decides which models perform well. They get promoted, and all of them which perform poorly after a few epochs, they get like deleted. And so you can decide how often do you want to run this process, and maybe also use Navasto building blocks to have something like this web app where you simply have a visualizer. How is my model selection performing, my hyperparameter search? So you see like how many models did I spawn? Are they promoted? How many times do they get promoted? This is like this rung you can see here. What's the loss curve? So you can just keep track and design your workflow as you want to do this. And when it comes to, let's say you have a good model, the best model, which performs quite well. Of course, you want to make fast predictions from it to really work interactively and work on this vision. Then you can decide how you want to do this inference. Option one is always a workflow. So as I said, you can load your existing model, you can load your new input, you can make some predictions, and you can simply save them on the hard drive, open them in ParaView and cite MetaPost. It's quite nice because if you use a GNN, you really have a 3D object. So you can rotate it, you can clip it, you can make some cuts. So be completely free, apply some threshold filters, ISO contour filters, whatever you want. But you can also like just create automated pictures like this, or visualize somehow the predicted drag values. So you get at the end predictions for everything you put into the training. But you also have some other options, like again, create a quick web app if you want to do this, or use a plugin, as you saw in the beginning with the Blender plugin. And for the web app, I mean, this is also an example we provide. At the end, you load a model, and then you predict for a new input. It's quite quickly. So again, you get a prediction. You can select which variable do I want to visualize. For example, the pressure, which is a good thing to visualize on the surface of the car. As it's a 3D object, you can rotate it. It's not learning on images, it's really learning on surfaces. You can also predict for the velocity, everything you used for training. You get information about drag values. If you can trust the prediction, like this confidence level, which is green for all the cars because we trained on cars. If I predict for a new input geometry like this, of course, I cannot longer trust this thing. And as I said, of course, you can also export this prediction. You can imagine as this prediction really it's a 3D object. So you saw like the list of available file formats where you can save this prediction. And once you did this, you can do whatever you want with it, like open it in another tool, like ParaView, for example, and play around, change color map, as I said, like clip it, slice it, create some nice vector arrow plots, something like this. So I think this is always the idea. So that both designers and also engineers can really work with this thing and understand what's happening if you change a certain feature. I mean, maybe to also close this circle, of course, you can also use the third option, the plugins, apply some morphing cages to this. You can also directly manipulate the shape. And again, like you see, like prediction is very, very fast. You also get always like a prediction confidence that says like a bit, can I trust this prediction because the network has seen something similar? Or is this really like an extrapolation where I try to make predictions for something that was not involved in the training so far? Right. So this is hopefully a good overview what you need to address if you want to train a graph neural network on hardware that is out in the moment and use really CFD data to create this input. And right, so a short overview. Probably some of you have some questions on the input provided here, so feel free to ask them, and thanks for listening.
Excellent, Jakob. Thank you so much. That was really, really cool. One question probably about the CFD simulations where you said you need 250 samples. Like, can that number vary, or where do you think it makes sense to start playing with graph neural networks? Like, when does it actually make sense? Like, once you collected a couple of high fidelity physics-based simulation, or what is the approach that you guys take?
Right. So this is like a question that we always get. How many samples do you need? And the answer is not easy because it really highly depends on how's the data set looking, what's changing in the data set. So also when we work with a new customer and he says like the customer has, let's say, 30 simulations, sometimes we have a super good model from 30 simulations. Sometimes we clearly see that we need a lot more samples because more things are changing. And let's say if you just have a data set where you have like some clear changes, then I would say 30 is enough. If you really have tiny changes on different areas of the car, I would say usually it's in the region of, let's say, 100 samples. But this is really just like a rule of thumb. It's a purely data-driven method, so it always depends on the data. This is the most important thing.
Got it. There was one question around the parameters, which I think you explained, like choosing a specific model, which then trains the parameters instead of doing it manually. How would you differentiate the difference between a GNN and traditional neural networks? Like, why are they so powerful, especially for CFD?
I think the graph neural network has a lot of advantages because it really takes into account not only the points, also the edges between those points. So let's say like a pressure information can travel over the surface and the network got an idea how the information is traveling, how certain changes really affect all the outputs. I think this is quite nice. So it does not learn like a Cartesian maps where you correlate some points with some output. It really has the connections in between. I think this is the major advantage.
Excellent. I think a follow-up question would be, where do GNNs excel compared to like the classical physics-based approach?
I think it's like a trait. I think graph neural networks or like especially AI models will never replace high fidelity simulations. But I mean, high fidelity simulations, they take some time. always. Even if it's like, if you can highly parallelize everything and have a super large HPC cluster, let's say it takes 30 minutes. And if you remember like this first picture, the vision with the interactive design, if you sit in a meeting and it takes 30 minutes or 1 hour, which is super fast for high fidelity simulation, but you cannot really make decisions. Whereas if you have the model, a new prediction really takes, let's say, 1 second or 2 seconds, and you can really play around and decide, is it worth fighting for a feature or not? And you can work interactively together. And you could also see it like, you don't have to trust all these simulations, not with the last few percentages, but it's like a recommendation system. Maybe put it like this, and you can maybe pre-select the most promising versions that you produced in this meeting, and maybe also like remove the versions that performed really, really poorly, which clearly point in the wrong direction. And everything that is interesting, this is something you can run a simulation on, where you really want to get like, let's say, the last few percentages. Because as I said, it's a bit of a trade-off. So I think AI models will always coexist with high fidelity simulation, because this is the power. You use the high fidelity simulations as an input. It's not like a low fidelity simulation. But you need it to train these models, and they will never replace it. So it's coexisting.
Yeah. Makes absolute sense. When do you use these type of models then? Like, where in the product development workflow do the GNNs fit, or like AI predictions fit? Is it usually before the design process or the concept phase? Like, how do you use them in practice?
Right. I mean, I think that you can really use them efficiently in preliminary design phases for a product. I think it's a no-brainer. But we also saw that people really use it like in the last stages of a product development process. So basically, you can use them. Or let's put it like this. I think they become really valuable if you have a lot of changes. Let's say you gather some last minute changes from another department, and you need to wait for them, but you can work on your product, because you can maybe get an AI prediction for different variants. So you are prepared. You can always work. You don't have to wait until someone delivers you a result, or the latest result. So
Yeah, that makes sense.
in all stages in the product design process where a lot of changes are done, there is really the value.
Yeah, perfect. Yeah, makes sense. I'm wondering, Jakob, you showed us a lot of examples of external aerodynamics. Is there also other use cases where you use GNNs apart from external aero?
Right. So the nice thing about these graph neural networks is they are physics agnostics. So it's not limited to like some certain equations that are used for the simulation processes. So basically you can apply the same workflow I showed to different scenarios, maybe conjugate heat transfer, maybe electromagnetics, some internal aerodynamics like compressor pumps, something like this. Because basically you have the same inputs. You have like a mesh, you have some result fields, and you have some, let's say, metadata, some scalar values. And simply you would like trade let's say, the pressure with a von Mises stress if you switch to FEA from CFD. So there's, at the end, like, you really need to think in terms of inputs and outputs, and you are not limited to CFD.
Perfect. That makes sense. There was one question. Can we control the object mesh shape or only the mesh count? Not sure what this question. Do you know what the person means?
I can imagine. So I would expect that really the shape of your product, let's say the shape of the car or the shape of the pump, this is something that was like specified by a designer. So if you want to train a model, I would recommend that you stick to the certain shape of the object. That's important, because this shape matches to the results. So I think this is like, the shape is the input, the results are the outputs. But if it comes to prediction, I mean, you are completely free. That's the idea. So there you are, welcome to really change the shape. But in a pre-processing step where you really pre-process your training data, it's I would say it's a requirement that the shape stays the same, that you don't lose features because you want to learn the influence of these features.
Got it. Makes sense. Okay. What about the interpretability of GNN models? Because you said it's physics agnostic, so it's kind to some extent it's kind of a black box, right? Do people really care? Like some of your customers, do they really care that it's a black box, or do they just want to see kind of this red, yellow, and green light where they can see, okay, I'm trusting the AI model's prediction, or is there some skepticism involved?
I mean, sure, there is some skepticism. So people always want to see that it works really for their particular data. And I always see it a bit like as the introduction of simulations really some decades ago. So I know like for CFD, it's computational fluid dynamics, but people said it's colors for directors. And when I started studying at the university, this was like people said something like this. And now it's like, it's clear that you use simulations because you're much faster, you can test more variants, and at the end it's like cheaper. It's the more efficient way to do this. And I think the use of machine learning models are inevitable. So it will be part of most of the engineering workflows in the future. But of course, you have some early adapters and you have some people that are really skeptical. But I think that this phase is like, I would say like 2 or 3 years ago. I would say since ChatGPT was announced, people are a lot more open to really use machine learning methods, AI models in their daily basis. And so it's like, okay, we need to adapt this graph neural network because there is not one graph neural network. We need to adapt this to the customer data set and then make it work. And then I think the skepticism vanishes. So this is what we see, but you have to keep in mind you can do a lot of things with a graph neural network. There are also different graph neural networks out there. This is why I also wanted to put this in today in the deep dive, that you really run a hyperparameter optimization. And let's say, okay, we have a lot of hyperparameters and you really take your time to optimize to the problem you want to solve. So adapt it to your needs, to your workflow, and then it's valuable. Otherwise, it's not. And there are also let's say for automotive, there are no foundation models out there because all the OEMs, they have their own simulation practice. And so it's like very special. So it's very tailor-made.
Yeah, this is why you guys are the pioneers out there. Regarding the workflow, Jakob, there was one question around how easy does it fit into existing workflows? Because as we know, people are skeptical. Maybe they don't want to disrupt existing processes. So how easily can you integrate NavPack or the API into existing workflows?
Right. I mean, we designed the API to really adapt to these workflows. So, I mean, I showed some snippets. So you can really work in Python. You can derive some compiled apps. You can derive some web apps. So this is something we really work on with the customer. So if the customer says, I want to work like this, my data is there and my model should be positioned here, then we simply make this happen and provide these building blocks.
Perfect. Okay, I think you've answered it. And last question from my side. You talked about data, obviously, which is the lifeblood of AI. When you start or think about using AI model or want to reach out to Navasto, do the physics-based models have to be from the same type? So if I simulate an LES, everything has to be based on LES, or can I mix different things? So runs, LES, for example, DNS, if I have data available, or do you guys recommend to always use the same baseline to then train the GNN?
Right. Basically, it's possible to mix and match these different simulation techniques, but I at least would really recommend that if you want to combine them, that you at least need to tell the network that you have different sources. Because let's say you have one input geometry, one input with some boundary conditions, and you simulate it using an LES or just a simple run simulation, or even some simpler ones, then you get some different results. So especially if some flow phenomena like flow separations are involved, I think this is a fact. So you can combine them. People like to do this either to upscale their data or have some multi-fidelity models. But I would always recommend to tell the network. And this is the nice thing about GNNs, because also on the input side, you have different possibilities. You can give the network some inputs, let's say, on a global level, something like a inlet velocity, ambient temperature, but you are also able to really give some other features, like some node values, some boundary condition fields, like a wall heat flux. Imagine for heat transfer, if you have batteries and they produce different heat fluxes. So this is like an input. And in the same way, you could also specify which simulation technique was available. So the network learns what's the difference between them, and then you can combine them. But as a general rule of thumb, I would always say you need to tell the network everything that changed on the input side. This is important. So please fully determine your system, then you get some good models.
Perfect. Excellent, Jakob. Thank you so much for this excellent presentation and answering all the questions. If you guys have any other questions, feel free to reach out to Jakob. I'm going to put every information down in the description of the video. And yeah, maybe there will be a second part or a third part in the future, Jakob. Thank you so much, and have a nice week.
Thank you too. And thank you for listening, everyone. Have a nice day.